Welcome to the video on amines. We will talk about the properties of amines and highlight some important reactions of amines, especially the fact that an amine is basic. We'll start off by recognizing that amines have this nitrogen, and the nitrogen is sp3 hybridized, but we have this lone pair. Right? And so the reactivity of amines is going to be a little different than anything we've learned so far. So the properties of amines. So amines that have three different groups coming off of them, including then the lone pair, would technically possess four different groups. However, we don't necessarily call it optically active because the truth is it can flip back and forth. And so if we had a fourth group on there in terms of a positively charged nitrogen, a tetrahedral nitrogen, then it could be optically active. But as it is now, the trigonal pyramidal nature of the molecule allows it to flip back and forth, and therefore it is not chiral. Amines with 5 or fewer carbons are going to typically be soluble in water. And also primary and secondary amines can form hydrogen bonds and have higher boiling points than hydrocarbons and even tertiary amines, because the tertiary amine has the nitrogen in the center here, and there's no NH bond that we could use for hydrogen bonding. But a secondary and a primary do have that NH, so we can have hydrogen bonding there, and you see that the boiling points are considerably higher. If we compared it to the alkane and to the alcohol, you see that the boiling point sits somewhere in between those. So oxygen is a better hydrogen bond donor and acceptor than the nitrogen because of the extra lone pair, but nitrogen still is capable. So amines are typically pretty stinky. They often smell like rotten or dead fish. Amines are bases, and this is something that we already know and that we can embrace at this point in this chapter. We have that lone pair that it can accept a proton from an acid. So it's a proton acceptor and it's a base. So another way of saying that is that amines can readily be protonated by strong and weak acids. It's useful to think about typical pKa of the conjugate acid of the base so that we get an idea of how reactive it is in terms of an acid. So here's some pKa values of some typical amines for your reference. Some notable things to mention on this table: that most amines, the pKa of the protonated amine, the conjugate acid of the amine, sit somewhere around 9 or 10. However, once you have a benzene ring, or if you have something that's aromatic attached to the nitrogen, you see the pKa of the conjugate acid goes down, meaning that it's a much stronger acid, meaning that it's going to be a much weaker base. Aniline, for example, benzene with an amine, has a pKa of 4.6. Even when we put methyl groups on that, we still have a pretty low pKa, meaning that it's a stronger acid and a weaker base. When we get to pyrrole, the protonated pyrrole ring becomes very, very acidic. And if you wanted to know why that is, it turns out that once we deprotonate that compound right there, once we deprotonate that, this molecule becomes aromatic. And so that makes it very, very, very stable, very, very weak base. And that's why we have that strong acid. It's because we regain aromaticity. With the pyridine, right? The pKa is about 5. So it's similar to the ones here with the benzene. And the reason this is not as low as the pyrrole is that we don't actually lose aromaticity when it's in the protonated form. In general, amines with more than 4 carbons are only slightly soluble in water. Solubility, of course, can be enhanced if we have an acid around. If we protonate that nitrogen and it becomes the conjugate acid or the cation, then it becomes much more water soluble because charge is going to be more soluble than neutral. And then the amines actually can easily be extracted from organic impurities using this idea of once we protonate, it will become charged and soluble in water, and then we can get it back by adding base to remove the proton to make it solid again. The pKa of most alkyl amine conjugate acids are between 10 and 11. Aryl amines are a little less basic because that lone pair can be delocalized, so they're more stable. The lone pair of an amide, so just for a second, we're going to talk about amides, and that's the C double bond O next to the nitrogen. So the lone pair on the amides is delocalized, and we actually have a pretty substantial contributor resonance structure, which indicates that there is a double bond in between the nitrogen and the carbon, making that bond a little bit shorter, actually. This is part of the reason why when we had amides in our carbonyl chapter and the carboxylic acid derivatives chapter, that it was less reactive because we have this resonance structure. So now if we do a quick review of the different ways we can make amines, primary amines can be made from alkyl halide in a two-step process. The first step is an SN2 with the nucleophile of CN minus. And so then we get this intermediate right here. Then we can very quickly reduce it using lithium aluminum hydride in excess, and then followed by protonation. So the triple bond gets reduced down to a single bond, and there we have our primary amine. In this reaction, you do have to remember that the carbon skeleton is actually expanded by 1. The second way we can form amines is from a carboxylic acid. So if we have a carboxylic acid and we react it with SOCl2, followed by an excess of ammonia, we end up with our amide, and then the amide can also very quickly be reduced down to the primary amine if we use excess of lithium aluminum hydride followed by treatment with water. In this case, the carbon skeleton is unchanged. We can also create aniline from benzene, and this is done by using the nitration of benzene. So recall that from electrophilic aromatic substitution. We have benzene, we make it to the nitrobenzene compound, and then we actually have two different ways where we can reduce that NO2 down to NH2. One is by using hydrogenation, so H2 in the presence of platinum. And the second is we can use iron, zinc, tin, or tin chloride in acid, followed by treatment with base. And so there's two different ways we can get to the amine or to the aniline. We can also prepare amines via substitution, where ammonia or the nitrogen lone pair is the nucleophile in the SN2 reaction. So we have backside attack, and then we end up with this protonated intermediate that we just then deprotonate using a second molecule of our ammonia. And then we end up with a primary amine. So it turns out that this is also a very common method to make the quaternary ammonium salt. So we just do what we just did a couple more times. The lone pair of the nitrogen is the nucleophile, backside attack, second methyl group is added, third methyl group is added, and finally the fourth methyl group is added for our quaternary ammonium salt. So another way is we can use azide synthesis. So we can convert the alkyl halide into an azide, and then we can reduce it to the primary amine. So in this case, we're using NaN3 as our nucleophile. It attaches, and then we can use again hydrogenation or lithium aluminum hydride to reduce that N3 down to the primary amine. The reaction is shown here if you're curious. The cool part about this reaction is that in the reduction step, we actually lose nitrogen gas, which is a driving force. In reactions of amines, we can have the amine be converted to an amide using an acyl chloride. It should be noted, though, that we need 2 moles of the amine in order to make this happen. You might recall this reaction from the carboxylic acid and derivatives chapter. Another thing I wanted to mention about nitrogens is that we can have heterocycles. So these are cyclic compounds that contain atoms of more than one element, including nitrogen. So here's just a couple examples. Both Nexium and Viagra have these heterocyclic compounds that have the nitrogen in the rings. Imidazole is a compound that is found in nature. It is in histamine, and it is in the amino acid histidine. Here's a review of a couple reactions that we covered in this video. So we can make primary amines from alkyl halides using NaCN, from carboxylic acids using SOCl2, and then from benzene using the nitrobenzene. And all 3 of these end up with a reduction step. So here we also talked about the azide synthesis at the top as a way to make another primary amine. There are several reactions that I did skip over from this chapter, including the Gabriel synthesis here, but I'll take this opportunity to let you know that I did kind of go a little easy in terms of this chapter, in terms of all the reactions of the amines, because I know we're at the very end and I wanted to give you just a little bit of a break. Amines are definitely pretty interesting though, and if you have time and you're interested, you could definitely take a deeper look in either of the textbooks and see if you can find something you're interested in. Awesome. Good luck. The end.